Okay, so welcome back to the same lecture. So we just covered our resonance forms, talking about that they are an average, they are a hybrid of these, right? And so we have the overall charge. So this is what you would draw our Lewis structure, right? It is an average of these three structures when you make a hybrid. And this is what it looks like. That solid line, those are single bonds, those are always there, but the dash lines represent the delocalized. So it can either be represented as a double or a single bond, but in reality, it's an average mix of those. All right. And so there we can see that's lowercase delta. That's a partial negative charge, meaning that, remember, each oxygen has a negative 2/3 charge. So it's not a full charge, but it does have a negative charge to it. It's a partial charge. All right. So which structure is best here? So A, B, neither is a good Lewis structure. Both are equally good. So for this one, this isn't drawn, but on A, if you look at A, our two oxygens that are going up and down, those should have charges, right? So the oxygens, that should have a -2 charge overall. And so we don't want to have that, right? So if you were to draw, and our sulfur in the middle, if you were to calculate the formal charge, would be +2. So it would be neutral overall, but you would have oxygen, sulfur, oxygen would have charges. And so when you draw Lewis structures, you don't want to have, you want to draw the structure that has the least amount of charges or neutral, right? So in B, every atom in there has a neutral charge. And so this is an important thing to remember. Once you get to the third period, so elements like sulfur and phosphorus, they can exceed the octet rule. They can have what is called a hypervalent structure. So that sulfur has 12 valent electrons, right? It has more than the 8 that's required. So in this case, essentially, it's fine. So B would be our best one. If you think about what is, in this case, neither is a good Lewis structure. You could argue that sulfur has more, but I would just go off what your instructor has told you. But B is a good one in the sense that every atom is neutral. And you want to minimize charges in Lewis structures. All right, so electron pushing with arrows. When you think about reactions and you think about what's actually happening when you're forming bonds, acid-base reactions, synthesis, decomposition, it's the electrons that are behaving and moving about. And when you talk about just about every type of chemistry, electrons are actually what make things happen. The only form of chemistry where we don't focus on the electrons is nuclear chemistry, because that happens in the nucleus. We think about protons and neutrons. But everything we think about in terms of our organic reactions, when we think about resonance structures, anything else like that, we are pushing electrons. We are moving electrons about. They are what make things happen. Arrow pushing highlights this. We show how the electrons are actually moving. All right. And so if you know how to draw these arrows, if you understand arrow pushing, you are going to do great. It is going to be a skill that you constantly need to, you're going to have to be doing these mechanisms for the rest of this semester and next semester. It is going to be a very important skill. So please practice, for those of you listening who aren't here right now. It is something you should always do. So the important thing to remember is that your arrows are showing the electrons moving, right? So that's the important thing. And there's a few rules that we're going to go through as we do this. So here is what the arrow looks like. This thing right here. When drawing arrows to create a new resonance structure from starting structure, arrows are like directions from electrons. Electrons drawn into their new spot in the next new structure. So you can think that when I draw an arrow, I am starting where the electrons currently are, and then the head of the arrow points to where the electrons are moving. All right, the arrow tells me where the electrons started and where they are moving to. I could be forming a new bond. I could be transferring electrons onto an atom. There's any number of possibilities. You just have to pay attention to it. But the important thing is your arrow starts at where the electrons are and goes to where they are going. You are only moving the electrons, right? So your atom should stay in the same position. You are not changing that in any way, shape, or form. Okay. Tail of the arrow starts where the electrons are being moved from. The arrowhead points to where the electrons are going to move. All right. So this arrow is just kind of like, here's where I started, here's where I'm going. Keep that in mind. Next up. Here we have this one. So when drawing arrows to create a new resonance structure from a starting structure, Arrows are like directions for the electrons. Electrons drawn into their new spot in the next new structure. All right, so they are showing what is happening. So in this case, if you look here as I do this, right now in the before, that oxygen has 3 lone pairs. Afterwards, I have 2 lone pairs. So that means that one of my lone pairs here is moving, right? When I look at a before and after picture, I need to see what's different. So before, my oxygen has a negative charge, my carbon has a plus charge, right? So I can think to myself, well, I know oxygen is negative when it only has 1 bond and 3 lone pairs. I know carbon is positive when it only has 3 bonds. But here in this side, right, my carbon is neutral, my oxygen is neutral. So here's what's most likely happened. My lone pair came down and formed the new bond. So I started at the lone pair. And when I go and point towards an existing bond, that means that I am creating a new bond. So now I have created that double bond. That arrow showed that the lone pair that was on the oxygen has now gone down and formed another bond between oxygen and carbon. And so now that carbon has 4 bonds, a double, a single, and a single. The oxygen has 2 bonds, the double, and the 2 lone pairs, they are now neutral. This is how your arrows work. All right, so this is what makes this work. Could it also go to the carbon as a lone pair? In this case, not really, because if you are doing that, you are transferring electrons between atoms, and you can do that in certain reactions, but in resonance, you can either basically those oxygen, if I moved it to the carbon, now my oxygen is going to be missing electrons. So you want to make sure that you are just moving it to that. So that is possible, but typically you can think of just moving one step away. We were going to talk about how this can work, but when you're going from an atom to a bond, that typically forms a double bond. All right. So let me just do this clear. All right. And so now, allowed curly arrow movements in resonance. What are we showing moving in resonance? So in this case, right, we had the lone pair move to a pi bond, right? So we are showing electrons moving, right? Don't forget, we're always showing the electron movement. And so we go from a lone pair to a pi bond, right? So in this case that we just did, right, in that example, we had that lone pair like this, and then we formed the double bond, right? So we had a lone pair like that. So don't forget, we are always showing the movement of electrons. So in this case that we just did, we went from a lone pair to a pi bond, right? So now we have pi bond to a lone pair. So we can go from a pi bond to a lone pair. So we went from a lone pair to a pi bond. So here we're going to go back onto the atom. And so now I'm going to draw on this atom. There's also a lone pair there already. It's not drawn, but it's there. That stays the same, but now I put that lone pair back on the oxygen like that. So I went from pi bond to lone pair. All right. Now I can do pi bond to pi bond. So I can go from a bond to the atom that's part of that bond, or I can jump over the atom. So my pi bond can go like this. And so now this is going to be my new pi bond. What is missing from here? This is very, very important. And I didn't do it in my top one. Something is missing here. I said that we are not changing anything about my molecule, meaning everything is still going to be connected, right? I'm not getting rid of any atoms. I still have the same number of electrons. But what is present in both the starting for B and C that I haven't accounted for in my product? We'll see if my one person, the charge, this is a very important thing. That is correct. Charge is always conserved in mechanisms. If you draw a mechanistic step and you go from one compound to the next, whatever the overall charge is for your starting materials should be the same overall charge for your product. There should never be a reason why that charge disappears. You have to watch it. So going back to here, and I'm going to change color to make this a little clearer, then I'm going to have that weird little line dealy. Here is a hydrogen. It's not drawn, but it's there. I'm going to put this hydrogen. It's still there. But now this carbon only has 3 bonds. Therefore, this carbon is going to be a plus charge. All right. In C, this carbon here has 2 hydrogens like this. And then this carbon has 1 hydrogen. So even after I finish this step, those hydrogens are still there, right? But now the carbon that lost the bond, that is going to be my new plus charge. So you can see that when I do this and I move my electrons, charges are going to move too, right? Now, I could go from something with charges to neutral, but just remember the overall charge of my starting materials. Yeah, this is just basically the idea that these are the electrons that are delocalized, but the overall charge of my material should always be the same. So if I have a plus and a negative charge, right, the overall charge of that is 0. So if I drew a resonance structure where the overall charge is still 0, it's going to be correct. So you just have to make sure that your overall charge is correct. It's constant. It is always staying the same. All right. Next up, electrons need to move where there's already room or room can be made by other electrons moving. So the important thing here, right, is that I'm going to come in here and I'm going to do something real quick. I'm going to draw the lone pairs on this oxygen right here. So what is the one rule that we have to keep in mind whenever we're doing electron pushing? Do you know what the one rule is that we always have to be aware of? It's one of the more important ones, and we have to pay attention to it. C, pentagon. Yep. Carbon cannot exceed. We have to remember the octet rule, right? Our atoms in the second period, carbon, nitrogen, oxygen, fluorine, those atoms cannot exceed the octet rule, meaning they cannot have more than 8 electrons, right? So as drawn, this compound here, every atom in this compound, the oxygen, the 3 carbons, they all have full octets right now, right? I cannot do anything to change that. I cannot exceed that. But imagine I come in here and I say this double bond moves to here, all right? So if I just drew that arrow, right, this is what I would get. What is wrong with this structure? Yep, that's correct. This carbon has 5 bonds. This is what we jokingly call a Texas carbon. It has more bonds than you're supposed to. So this is a bad resonance structure because I moved electrons in a way that's perfectly fine, but I still have to make sure that I don't violate that. So what can I do if I move that first bond? What is something that I can do? A mechanistic step can have more than one arrow. Is there anything I can do at the same time? And I'm going to draw this arrow just a little bit cleaner. Is there anything I can do to make it a little bit better? I can move this double bond up to oxygen and have it become a lone pair, right? So now there was 2 lone pairs here already, but now I put a lone pair up there, right? And then something important to remember is that this carbon had 2 hydrogens, not drawn, but they are there. They're not explicitly shown. And then these are still here. So if I look at my starting compound, the overall charge is 0. Every atom is neutral. But now this oxygen here has 1 bond and 3 lone pairs. If you remember, that is going to be a negative charge. This carbon only has 3 bonds, therefore it is going to be a positive charge. What is the overall charge of my compound after I drew the arrows? -1 plus +1 is going to equal 0. My charge is still conserved, right? There are charges present, but when I add up all of the charges, it still equals 0. And that's what I mean by having charges conserved. I can move things around as long as I'm not violating the octet rule. Electrons are going where they can move. I'm making room for them and stuff like that, provided that I didn't break any rules and I didn't exceed the octet rule. And also that I still have an overall charge of whatever my starting compound was, then I haven't broken any rules. This is correct. This is completely fine. All right, so hopefully that makes sense. Okay. And this is just the basic idea of arrow pushing. So make sure you keep an eye on that. So here we have lone pair to lone pair, right? This is the idea of where you can do lone pair to lone pair. So I think this is what you were asking earlier. But typically you want to do it between atoms that have that there. So if you were to do this, this is basically the idea of where you're just moving from lone pair to lone pair. So we would say that this goes like that. And then that's going to go to here, right? And then we can go lone pair to pi bond and then to lone pairs. So I can come down to here and form a pi bond like this. Right? And now I can move this pi bond up to here. And then that is going to give me that. So you can see earlier when you asked the question, can I move lone pair to atom? Yes, I can. But in reality, there was this hidden step that was happening, right? We were still moving it one step at a time. But we can do that. So don't forget that when we do resonance, sometimes there are hidden steps there. All right. Yes, fun. Yep. And the important thing you want to remember, this is something I have seen so many bad chemistry teachers do. None in NAU. NAU organic professors, they're sharp. But sometimes you'll see this. One of the fundamental rules, we don't violate the octet rule, right? We maintain our charges. And the last and probably the most important rule, never break or form a sigma bond in resonance. When we are doing arrow pushing for resonance, you do not break a sigma bond. The sigma bonds are our structure. They are our skeleton backbone. You do not break any of them. You do not form new ones. Every atom should always be connected. You're never going to break anything in a resonance structure. All right, that's the important thing. So an example of this, of what would be a bad example to do, would be something like, say, this. So imagine you had CH3 connected to OH like that. There really is no other resonance form for this structure. But if you did something like that, where you moved a single bond, so you ended up breaking it, and then you ended up with CH3 plus like that, and then OH with a 3 minus, this is completely wrong. Never break a sigma bond when you're doing resonance arrow pushing. When we get to mechanism arrow pushing, different story. But for right now, with resonance arrow pushing, never break that single bond. Yeah, that's just wrong. I have seen professors do that before in other classes. Not at NAU, like I said. They're sharp. They know what they're doing. Okay. So which of the following are possible resonance structures of this one? So I will let you take a few seconds. Which of these are possible Lewis structures? So it's not just me. There is someone in here with me in this video. So I'll see if they have an answer. Which of these are possible Lewis structures for this one, or possible resonance structures? Let's see if they come up with an answer. Maybe yes, maybe no. So you're saying, okay, they're saying, so you're going to say either letter C or letter D. All right. So one way you can always check how to do this is just think to yourself, can I move arrows in such a way to get what I'm looking for? So if I go from here to here, right, then I move this onto this carbon like that, that is going to give me A. I haven't violated any of the octet rule. All of my atoms always have 4 bonds or 3 bonds in a lone pair, so I haven't gone above, so A seems to be relevant. All right, so now for the next one, let's take a look at it. So if I bring this lone pair to here and then move that double bond up to that oxygen, that is going to give me B. B appears to be correct. Again, I didn't violate my octet rule. I'm only moving electrons. All right. So for C, I'll pick, we'll go with black. So looking at it, it looks like if we have here, this moved to here like this, right? But one thing I want to add is that there are two hydrogens here, right? So when I do resonance, I cannot break sigma bonds. So those two hydrogens are still going to be there. So if I draw my hydrogens in this scenario, that carbon now has 5 bonds. This is a bad resonance structure, right? The movement of the lone pairs was fine up until I got to that carbon. I cannot move anything off of that carbon. I cannot break any bonds, so this resonance form is bad. And finally, for the last one, we'll do green. Green's a good color. Take a look at it and say this double bond moved up to here like this, and that appears to be correct. I haven't violated the octet rule, so the answer is going to be A, B, and D, the letter C. So this is how you check to do it. Now, I'm old and I've done this so many times. I have taught this class since 2012. I know how to do this quickly. You may be saying, that was fast. Well, maybe not. Some of you may be saying, wow, Dr. V, you're really slowing down in your old age, and maybe I am. But the idea here is that this just takes practice. And if you practice doing this and looking for it, so don't forget, don't violate the octet rule. Only move electrons, right? And always make sure you are maintaining the overall charge of our compound, right? So in every one of these, it's neutral if you add up all the charges. Okay, so this is just practice. I know what I'm doing. I've been doing this for a long time, and I probably have done this problem at some point, but this is just the idea. Practice, 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 practice. All right. It's enough of me saying practice. You hear me say that enough. Okay, next up. Preference 1. Most important form has maximum number of octets. So remember, the octet rule is one of our rules that we like. So when we draw a Lewis structure, right now as drawn, does every atom in this structure have a full octet? So hydrogen only needs 2. It's good. Hydrogen 2, oxygen has 2 bonds, lone pairs, but this oxygen only has 3. This is a bad resonance form, only in that not every atom has a full octet. Think about, is there a way that I can do a resonance form so that every atom will have a full octet? So think in your mind, try to see if you can do it. You can hit pause. What I can do is that this lone pair can come down like this. So now my resonance form, I have, my carbon still has the hydrogens, right? There is now a double bond. The oxygen only has 1 lone pair, and there is a hydrogen. So hydrogen, something that's changed. I can't break my sigma bonds. Oxygen still now has 3 bonds and lone pair. It's good, but it's going to have a formal charge of plus. Carbon now has 4 bonds. So if I think about charges, oxygen does not like a positive charge because it's electronegative. But if I had to choose between a full octet or an atom having a charge, you always pick the full octet. So this version here, and I'm going to erase the little check mark so you can see it. The version on the right is better because every atom has a full octet, all right? Preference 2, if a resonance form must have a formal charge, the most important contributor has these charges on the atoms willing to accommodate them. So when we say willing, we say which atom has a preference, and this is where electronegativity comes in. So the atom that is the most electronegative is going to prefer to have the negative charge. So here, if I look down here, the first thing I want to check is, well, full octet. So if I turn on the writing tool, full octet. This carbon has a full octet. Carbon has a full octet. Carbon has a full octet, right? All of the main players all have full octet, so it's good. But right now, carbon has a negative charge. Is carbon the most electronegative atom in my molecule? The answer should be no. Oxygen is going to be my most electronegative atom. So I'm going to see, is there a way I can play with my electrons, if I can move my electrons around to get that negative charge to oxygen? So when I come in here and say, you go here, and then you go here, and I draw this, and don't forget, you always draw a 2-headed arrow when you do resonance because going back and forth, it can go back and forth between those. Right now, There is a double bond down to here to that CH2. The CH3 is really not involved, but it's still down here. It's chilling out. It's like, hey, what's up, bro? But now this oxygen has a single bond, and now it has 3 lone pairs. So if you remember, an oxygen with 3 lone pairs and a single bond has a negative charge. Still have the same overall charge, have not violated the octet rule for any of my atoms. This one on the right is going to be preferred. So if you can put the negative charge on the most electronegative atom, that is always going to be preferred. Now, that doesn't mean that the negative charge automatically goes to the most electronegative atom. The electrons still have to be able to move there, right? And they have to be able to make that move. If they can't move there in a normal way, then it's not going to work. Okay. Go ahead and pause if you need to grab this stuff. I'm going to hit clear. Take a look at it. So remember, when you're doing preferences, full octets take priority. If you have to have a formal charge, you want to put the negative on the most electronegative atom, and you want to put the positive on the least electronegative atom, right? You can have a plus, you can have a minus. So this is important. Okay, next up, preference 3. The most significant contributor, meaning when we think about we're making the hybrid evolve our resonance form, like which one is the closest in terms of which of these actually looks like my actual molecule, is the contributor that has the maximum number of covalent bonds. So if I look here and say, well, which of these has the most covalent bonds? If I look between these two on the left and the right, the one on the right has 1, 2, 3, 4, 5 bonds. The one on the left has 4. Therefore, on the right should be my biggest contributor. Additionally, all of my atoms have full octets. That's also a key indicator. So the one that has every atom with a full octet is usually my biggest contributor. Okay. Finally, preference 4, the most significant contributor has the least formal charge. So what I can do here, because why not? Why not make things fun, right? Is that I can move this onto this like there. So now I have C here. That was odd. What does that? So right now, this carbon has a plus charge. This carbon has a negative charge. And so I can have charges, but when I think about what is the biggest contributor, it is the version of my resonance, the resonance form, where I minimize those charges. So right now I have a plus and a negative. So 2 atoms have charges. Here on the left, there's no charge on any of my atoms. The one on the left is going to be my biggest resonance form. Also, I want to point out, I moved the, excuse me, lone pair onto the one on the right. I could easily have done that and moved it to the one on the left, right? So there's going to be 3 resonance forms here. But this here in what we're starting point, that is going to be our biggest contributor because A, every atom has a full octet. B, I have maximized the number of covalent bonds. C, I have minimized the formal charges present on all of the atoms. As these things add up, as I follow all of those rules, whichever one of my resonance form meets those requirements, that is going to be my biggest contributor. Meaning, if I was to actually look at the structure, it most closely resembles that one, right? That'll be my biggest contributor. It is the most stable form of my resonance structure. So that's a common question to say, what is the biggest contributor to the resonance? And you have to figure out what is a way to draw my Lewis diagram in which that molecule is the most stable. Okay. Any questions from my large audience? I say large, but it's just one person and she's very small. I think I'm probably 3 times her size. She's a very small person. That's okay. So now coming here to our next page, preference 5, the most significant contributor will have the least number of unpaired electrons. So this is going back to the idea of number of bonds plus lone pair electrons. So you want to maximize the number of shared electrons. You want to minimize the number of unshared electrons. And that's always going to be the case there, right? So just remember that one. So here is our example. For each of these 4 things, I'm going to label them, and I'm just curious to see if any of you guys can figure out. So we're going to go to I'm going to move my little bar here real quick. So I'm going to come to this first one and say, again, I have to move the bar because it's taking up space. So in problem 1, which resonance structure is the most stable, 1 or 2? Remember, you have all of those different things to consider. Which one is going to be our most stable or the biggest contributor? Those preferences went in order. So what is the most important rule that I constantly said you always have to make sure you do? It's the big one. Full octet rule. 1 does not have a full octet. The carbon on the left doesn't have a full octet. It has one on the right. This is going to be my bigger contributor. Even though there are charges present, it still has the same overall charge, but now I've also maximized the number of covalent bonds and I've minimized the number of lone pairs. Nope, oxygen, when it has 3 bonds and a lone pair, is positive. When oxygen has 1 bond and 3 lone pairs, when you flip that ratio, that is when you get that. Okay, let us go to our next one. Let us do number 2. Again, why it does that, nobody knows. My computer hates me. Maybe I need to clean off the screen. It's been a while since I've done that. If I have this here, which one of these is my biggest contributor, 1 or 2? Which one of those is my biggest contributor, 2? Right? But what's wrong with 2? There's only one thing wrong with 2. Don't have a full octet. 1 has a full octet. So octet, always got to pay attention to the octet. 1 is going to be my most important one. Also, I have maximized the number of bonds, 1, 2, 3, 4, 3 on the right. On the left, if I drew my lone pairs, there are 2 lone pairs. And on the right, there are 1, 2, 3. So 1 literally checks off just about anything. I minimize the charges. I have the most number of things. Yes, octet rule is always the biggest thing that is going to matter. All right, let us go on to our next one, and I'm going to move things about. Full octet is always our biggest stability. Okay, so I'm going to change color. All right, so now if I look at this one, which one of these is my most stable, 1 or 2? Which one of those is my biggest contributor to my daily, 1 or 2? Yep, the answer here is going to be 2, and that is correct because in 1, they both have full octets, right? There's no difference there. I have the same number of lone pair electrons, so 1, 2, 3 here, and then 1, 2, 3 here, right? And then, that doesn't change. I still have 4 covalent bonds. The only difference is that I have a negative charge on the carbon versus a negative charge on the oxygen. Oxygen is more electronegative. If I have to have a negative charge, it wants to be on the most electronegative atom. Therefore, 2 is my correct one, right? 2 is my correct one. All right, and finally, our last one here. Which one of these is going to be the biggest contributor, 1 or 2? So for our last one, which one of those is the biggest contributor, 1 or 2? All right. So is there anything wrong with 2? Is there anything inherently wrong with 2? What's the big rule that we always want to make sure we meet? It's that what rule is always met first? It's that we have a full octet, right? So in 2, we don't have a full octet of that carbon. Here, everything has a full octet, right? We have 4 bonds in this one. We have 3 bonds here, so 1 is a little bit better there. There is going to be 1 lone pair here versus 2 lone pairs here. So we've minimized the lone pairs in 1. That means that. The only thing that is inherently wrong with 1 is that the positive charge is on the oxygen. It's better to be on the carbon, but if you have an empty octet and not a full octet, then that's not going to be great. So octet rule trumps all. Yeah. Okay. Hopefully you guys at home, those of you participating at a later time, hopefully you got that and that all makes sense. All right. Next question. It's always good that we have all of these. Our next question reads, which of the following resonance structures contributes the most character to the structure of the overall resonance hybrid? So these are all correct resonance structures. Which one of these contributes the most to the overall resonance structure? So take a look at this. Try to figure out which one of these is going to be my best contributor. Think about that as best you can. Give you a minute or so, or whenever you come up with an answer. Okay, so it looks like C seems to be the answer that we're going with. So let's just take a look, right? Octet rule is going to be our most important thing. So I'm going to take a look, because why not? Why not make life more difficult? In A, this nitrogen does not have a full octet, right? That's not, actually, hold on. Let me do that again. There's a hydrogen. Nope, that nitrogen does not have a full octet, because if you did the formal charge, right, you are missing, actually, real quick, I'm going to do one thing, because I realize that there is just one thing missing from here. And then I will say ask it again, because I think this is just a small thing, but I think this is just something that happened. That nitrogen, in order to have a negative charge, needs to have 2 lone pairs. There's actually 2 lone pairs on this nitrogen. There's 2 lone pairs on that nitrogen. Now, I'm not saying what your answer was right or wrong before, but that nitrogen, again, has 2 lone pairs. And I'm going to put a second lone pair here, because there needs to be one like this. In order for nitrogen to have a negative charge, it needs to have 2 lone pairs. So that is going to be that. So which one of these appears to be correct? Which one of these is going to be the best contributor to the overall resonance? All right. And still, we still have a C. So if I look at them, are there any of these that have empty octets, right? So in D, this carbon doesn't have a full octet. In E, this carbon doesn't have a full octet. In B, this carbon doesn't have a full octet. So going to remove those from consideration, only because those appear to be not great for my resonance, right? So that's something that's true right there. So we don't have this full thing going on. Next, when I think about this here is that between A and C, every atom has a full octet. The only difference is that when I draw my resonance, this lone pair goes to here to form a double bond, and this goes up there, right? And it's the same idea where there's still a lone pair here. So this would come down, and then this would go there. So these between these two resonance forms like this, like that. Those are the two things. And basically the idea here is that every atom has a full octet, right? My charge is still conserved. I haven't violated that. I have maximized the amount of bonds. I have minimized the number of lone pairs. The only difference is which atom is more electronegative. And oxygen is more electronegative than nitrogen. So that's going to prefer to have the negative charge. My correct answer should be C. C should be my correct answer because I have minimized charges. Every atom has a full octet. I have maximized the number of covalent bonds. I have minimized the number of lone pairs. If I have to have a formal charge here, and I put that on the most electronegative atom. Therefore, C is my correct answer. Hopefully this is starting to make sense to you guys. Hopefully you're like, yes, I get it. Eureka. But practice, 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 practice. All right. Yeah. Do the chef's kiss, We'll do that. All right. So what, if anything, is wrong with the resonance structures below? What, if anything, is wrong with the resonance structures below? What is wrong with the resonance structures below? If you can tell. Can you see anything wrong with the resonance structures? So remember, when we draw our friend, Mr. Arrow, we'll call him Mr. Arrow, why not? Our arrow, right, shows us where the electrons started and where the electrons end, right? So in this case, that means if I'm doing this arrow, this pi bond is moving to this location. However, if I do that and I look at it, yes, that pi bond is moved correctly, right? But the important thing to note here, and maybe you missed it, this lone pair is no longer there. Now it's here. It moved locations. This would be a bad arrow, right? Because even though my pi bond moved to the correct place, my electrons literally jumped locations. It went from a lone pair on one carbon to 2 carbons away. So my arrow is wrong. All right, so if I was to draw this, and I will draw this in a simple form, I'm just going to draw this as CH3, 2 carbon, double bond to carbon CH2 like this, where I have this H like this and lone pair. The better arrow would be that this moves to here, this moves to there. Now that is the correct arrow pushing, right? I can't have electrons teleporting, right? When I do my arrow pushing, they have to move in a line. Think about it as a waterfall. My electrons have to follow a pattern. I have to draw the arrow. If they move and I have no arrow representing that, that is a bad resonance form, or that I didn't do my arrows correctly. Again, just practice, you have to look out for that. So if I didn't change anything else, if I'm moving things and my arrows are showing which electrons are moving, then it's a good arrow pushing thing, but you've just got to keep track of everything. And again, just practice. I promise it'll get better. It'll get easier. Life becomes a little bit easier as we practice with most things. Like me in the morning, I can make my breakfast very quickly because I've been doing it for many years. Coffee's always ready to go. So here's where we're coming up to. And so it says here, this is our resonance pattern recognition. There are 5 general bonding patterns in which resonance occur. If you can recognize these patterns, you can recognize whether or not, you can predict whether or not resonance will occur. So you may not know what all of these terms are, but I believe we go through them on the next few slides. Allylic lone pairs, meaning are the lone pairs close enough? Allylic carbocation. A carbocation is a carbon that doesn't have 4 bonds, it only has 3. Lone pair of electrons adjacent to a carbocation, a pi bond of electrons between two atoms with different electronegativities and a conjugated pi bonds in a ring. The only way to recognize these patterns is to do lots and lots and lots and lots of practice problems. Because remember, what I've told you guys since the first day I met you over a year ago, I've known you guys for a year, which is pretty great. But what I told you guys a year ago, never do problems. Don't do problems until you get them right. Do practice problems until you cannot get them wrong. If you do more practice problems, I understand you're a college student. I've been where you guys are. Time is a huge commodity. Sleep is so fantastic. Doing nothing is so fantastic, right? You always want to make sure that you're doing as much practice as you can, because there's only so many ways that we as chemistry people can ask you this question, right? There's only so many different ways. And if you begin to recognize these patterns, your life becomes easier. And again, I understand time is a commodity. You have relationships, you have friendships, you have TV shows and movies you want to watch and read, but practice is always important. Just practice as much as you can. And these are the 5 big things that you will start to recognize and say, aha, I know what that is. I recognize that. That means that there's probably resonance, right? And again, just keep at it. So now that we know that, we're going to introduce a general idea. So we have something called vinyl and allyl, and we use the term vanillic and allylic. Vinyl means that I have the pi bonds are next to each other, right? To the atoms of a pi bond. So if I'm referring to the carbon, they're both part of that pi bond. I say that the carbons are vanillic to each other, all right? So the carbons in the pi bond, those are vanillic. Allylic means that I go past one carbon to here. This carbon is allylic with those 2 hydrogens, all right? This carbon is allylic to those 2 hydrogens. It's not the next atom, it's 2 atoms away. That's what allylic is. It's 2 atoms away. Vanillic is next to it. It's part of that pi bond, right? So we look for allylic lone pairs because they will be resonance delocalized. So these 2 nitrogens here, call you nitrogen 1, call you nitrogen 2. Nitrogen 1, I look for allylic. So if I look and I say, is there something, right, 2 atoms away, if I can move them, if they're next to it, right, if they're adjacent to it, nothing here, nothing here, this is not allylic, but here, right here, right, it's allylic. That is an allylic position. Again, this is just practice. You can see that we have a lone pair, and then we have a pi bond. That nitrogen is allylic to that double bond. All right, it is adjacent to it. That is allylic. All right, so the nitrogen on top is not allylic because it's not right there. All right, this will make more sense as you practice it. Okay. All of the lone pairs shown below are allylic. So if you look here, 1 away, 1 away, 1 away, 1 away, right? They are allylic. So when you do allylic movement, you are going to always do 2 arrows, right? And so you can see there, all the arrows are there. So when you make an allylic movement like this, you are moving it. So the electrons are, so if we start here, right, and I draw what's below, now my new thing is going to be here. My electrons have moved 2 atoms away. Again, if I draw this, oh, sorry about that. Draw that again. Here, the lone pair electrons now have popped up on an atom 2 away, right? They're not the same electrons, but I have moved electrons, lone pair, onto an atom 2 away like this, right? So this is just the idea that you're moving your electron, like they're essentially shifting 2 atoms away onto that atom. And this is allylic. So you'll begin to recognize these things that are allylic, right? When the atom with the allylic lone pair has a negative charge, the charge is delocalized with the lone pair. So these are all resonance forms, right? The actual hybrid of all of these is going to be the correct thing. So in our first one, the carbon on the right has a negative charge, carbon on the left has a negative charge. The hybrid is an average of those, right? Same thing with the rest of these. If the allylic atom is neutral, then it will become positive, and the atom receiving the lone pair will become negative. So you can see we started neutral. Now when we remove our electrons, the atom that donated the lone pair to form a new bond becomes positive. The atom that received the lone pair becomes negative. All right. So again, the atom that donates the lone pair is going to become positively charged. The atom that receives the lone pair, that is going to become negatively charged. Donates becomes positive, accepts becomes negative. And that is a trend you are always going to see when you do this allylic movement, right? Okay. So in our first one, you may be saying, well, I don't see that. Well, here we start negative, right? And it donates. And if I go one up, if I add a +1 to it, it becomes neutral, right? This received the electrons, it now became negative, right? So it's always going to change. That charge change is always going to happen the same way, all right? And again, you will see this the more of these problems you do. It'll become second nature. All right, so now, what functional group is located at the indicated point in the structure below? So now we're coming to functional groups. So functional groups are very important. Can you tell me why functional groups are very important? Yeah, so functional groups have different reactivities, all right? Every functional group that we think of has a different reactivity. So if I take an alcohol and add it to a carboxylic acid in the presence of a H plus catalyst, I will form what's called an ester. If I take a primary amine and an acyl chloride and I add them together, I'll make what's an amide, right? So you're saying, like, what does that mean? It means that if I take certain functional groups and I mix and react them, I will form certain products. If I know what my functional groups are, if I can start to recognize them, I can start making behaviors. Because remember, like what we said last year when we started learning Lewis structures, if I understand the connectivity, I can predict behavior. If I know what the functional group is, I know how that compound is going to be reactive. So in this case, our arrow is pointing at a carbon that is double bonded to an oxygen and a hydrogen and a carbon. If you are double bonded to an oxygen, a single bonded to a carbon and a hydrogen, you are what we call an aldehyde. This is an aldehyde, all right? For your information, just so you guys know, there is no ketone present here. There's no ketone in this molecule. If I have a carbon double bonded to an oxygen, single bonded to an oxygen, that is what we call an ester. If I have a carbon, or if I have an oxygen that is single bonded to a carbon and a carbon, that is what's called an ether. And we do not have a carboxylic acid present, all right? As you go through, you are going to learn what these are. A ketone, in case you were wondering, is going to be an oxygen double bond. So it's a carbon double bonded to an oxygen and a carbon like this and another carbon. So the idea here is that instead of a carbon and a hydrogen single bonded, it's two carbons. That's what a ketone is, like that. And again, I would look in your textbook for the functional groups and make flashcards. Draw what is in each of these functional groups. I can look at these and I say, I immediately know, okay, aldehyde, aliphatic carbons, ether, ester, alkenes. So I know what they are. So flashcards are recommended for these. And this is something I'm going to tell you right now. The more that you commit to your mind in terms of functional groups and reactions and flashcards, if you start building that pile now early on, your life is going to be so much better. To those of you listening, I promise you, flashcards make life easier. Also, another thing I recommend, colored pencils. They can help you keep track of things. I like to use them when I draw my mechanisms. This is why when I change colors, it's a lot easier to see because I can relate one color to one thing I'm doing. So I recommend colored pencils when you're doing practice problems as well. Flashcards too to help you with your functional groups. All right. So now going on, allylic carbocation. So if I have a carbocation and then I have a double bond, I can move it over. So you can see here, when I have this thing, I am essentially moving my double bond, and my carbocation, if I was to number carbons 1, 2, 3, 4, 5, 6, my carbocation is on carbon 1. Here it is on carbon 3. Here it is on carbon 5. I am shifting that carbocation 2 carbons at a time. It was on 1. I do my first arrow pushing. It is now on 3. I do my next arrow pushing. It is now on 5. This is the trend you see with allylic carbons, is that you are moving charges 2 atoms away, right? And this is just something you have to keep on. So a total of 3 resonance structures for this allylic carbon. And again, when you see this, you'll be able to recognize it a little bit better, okay? A lone pair adjacent to a carbocation, right? So I have an atom with a lone pair. That oxygen has 3 lone pairs. Attached to that oxygen is a carbocation. I can move resonance lone pair down and form a new double bond. Same thing with the one below. It's the same idea, right? I can move lone pairs down to form double bonds onto an atom with a carbocation, and this is going to be allowed, right? Because now if you look in my first one, I have a negatively charged oxygen and a positively charged carbon. After I do my arrow pushing, there are no formal charges. In both cases, the overall charges add up to 0. In my second example, I have a carbocation, I have a carbon with a plus charge. After arrow pushing, I have an oxygen with a plus charge. Don't forget, charges are always conserved. That is a good indicator of whether or not you successfully moved your electrons. If your charges don't match up for some reason, double check, say, what happened? Did I do a formal charge wrong? Did I do something wrong like that? That is going to be your best indicator in terms of, okay, did I make a mistake? All right. Next up is a pi bond between atoms of different electronegativity. So I have a pi bond between an oxygen and a carbon, and oxygen is much more electronegative. So I can move that double bond onto the oxygen, and now I have created this resonance structure. My overall charge is still the same. However, I made a carbocation. So basically, the hybrid, my actual hybrid of both of these, is that it is a sharing of this. So my oxygen is going to be partially negative. My carbon is going to be partially positive, right? And that's just because we have an unequal sharing. This is a polar covalent bond. And again, this is our next example of that, right? And finally, conjugated pi bonds in a ring. This is something called benzene. We've talked about benzene before, but if you notice, I just move my double bonds around, right? Goes there, there, there. Nothing has changed besides the location of the double bonds, right? And this is something that you're going to learn about a little bit later. But if you notice, everything still stays the same. Every carbon still has 4 bonds. My actual benzene compound is a hybrid of this, right? All of those electrons inside are delocalized. And this is something called an aromatic compound. You're going to learn about a little bit later, so don't worry about it. But it's the same idea. Again, if you have conjugated pi bonds in a ring, conjugation just means you alternate between double, single, double, single, double, single, right? You see those alternating double, single, double, single, double, single, and I end up right back at the start. That is a nice conjugated system. So that's going to be it there, right? And this is the last example of that if you see this. All right, so there is a summary of the 5 main patterns. Again, I would recommend print out this slide, have it next to you when you're doing your practice resonance problems and identifying, and see if any of them meet these requirements. See if any of them have this. If you can recognize these 5 patterns, this will save you time and say, yes, there has to be resonance here, right? And so if you can recognize this, that'll make your life easier, right? So next up, what functional group is shown below? And I did this on the last one. When I have an oxygen, right, attached to a carbon, that is going to be an ether, all right? Ethers are a form, we can use ethers as anesthesia, right? Like an anesthetic. The very first one that we used successfully was diethyl ether. So that was one of the first things. So up until about the Civil War, if you had to have a limb chopped off or teeth removed or cancerous cysts removed, they pretty much just gave you some booze, had you bite down on a piece of wood and said, well, here's hoping you survive. But but this is the idea of what an ether is. And so carbon, oxygen, carbon, those single bonds, right? That is what an ether is going to be. And again, you can look in your book for these functional groups, or you can look online. You can probably find something online that maybe you can even make for your flashcards. I wouldn't be surprised if you couldn't find anything. All right. So it says, practice the act of recognizing the patterns of resonance and using curved arrows to push electrons and show their delocalization. So there's all sorts of things happening here right now, right? You have double bonds next to lone pairs. You have lone pairs next to carbocations. You have allylic positions. There's all sorts of things happening here, right? There's all sorts of things that you can do that. So you can, sorry, I'm laughing at a comment. You can look at all of these and say, aha, I recognize these. So practice this one. I'm not going to do it for you because I think this is good for practice, all right? Finally, delocalized lone pairs. Localized electrons are not in resonance. They are localized. They are stuck where they're at. Delocalized electrons are in resonance, right? And they are more stable, right? We talked about this. The more resonance you have, the more resonance forms you have, the more stable you are. To be delocalized, a lone pair of electrons must be adjacent to an atom with an unhybridized p orbital. So if you think back to your hybridization, right? Because I know you guys think about hybridization all the time. Change colors here. I have this atom with a lone pair. What is the hybridization of this carbon? What is the hybridization of this carbon? sp2, yeah, the hybridization of this carbon is that this carbon here is an sp2 hybridized, right? I have an unused p orbital. If I have a lone pair next to an sp2 atom or an sp atom, that implies that those electrons are delocalized. Essentially, those electrons can slide into that atom's DMs. They can just smooth on over, right? So if you have an atom with a lone pair and it is next to an atom that has unhybridized p orbitals like sp2 or sp, those electrons can move over there. This means that these electrons are delocalized. This implies that there is resonance. And so this is what's happening. So the oxygen here is also sp2. And so if I was to draw this after the resonance, right, after I move my nitrogen here, like this, I move my electron, so plus, and then negative like that. I still kept my charges. And that's just a general idea. If you recognize that my electrons are delocalized, they are in resonance. Resonance adds stability. This is a very stable compound. In fact, this is what's called an amide. This is actually what an amide is. A carbon double bonded to an oxygen, single bonded to a nitrogen. This is an amide bond. This is the bond that holds together all of your peptides, which makes up all of the proteins in your body. These peptide bonds, which are the same thing as an amide bond, this is what this is. This is how you make this. To break these, you add water and acid, which you have abundant amount, or free protons in your body. And amides are fairly stable, and we want them to be fairly stable, right? We want them to be able to hold up to the rigors of your body, but they can be broken down because you don't want proteins to last forever. But this is just the idea. All right. Okay, in one structure, there you go. You can see I moved them over. The lone pair moves over. The lone pair is delocalized, right? I have successfully moved it over. So now, since that nitrogen is part of that resonance structure, meaning I have successfully moved my electrons, right? What does the hybridization of this nitrogen, what does the hybridization of this nitrogen look like right now? What does that hybridization look like? Well, don't forget, you include the number of bonds and the number of lone pairs. So how many things you're connected to. So this nitrogen has a lone pair. It's connected to this R group, to this R group, and to this carbon. So it's connected to 4 different things. Right now, it looks like it's sp3, right? This is what it looks like in this structure. However, when I look at after I do my resonance, after I do my arrow pushing, now this nitrogen It's connected to an R group, and to this carbon. Now it has sp2 hybridization, right? And you're like, wait, on the original one, it looked like it's sp3. On the hybridized one, it looks like it's sp2. What is it? If it is part of that conjugated system, if it's in resonance, that means it has to be sp2. This has to be sp2. So if you see an atom that's like, here it's sp3, here it's sp2, it's always going to take the hybridized form that is missing a p orbital. So you're going to go to sp2, right? The lone pair is delocalized. The nitrogen has to be sp2 hybridized. All right. That's what's happening in our resonance. This is sp2 hybridized. That's correct. Yep. That is a 100% correct thing, is that as you increase the S character of an atom, it becomes more reactive. So sp is more reactive than sp2. sp2 is more reactive than sp3, and that is because you have greater electron concentration. But we're going to get into that when we get into something called molecular orbital theory and atomic orbital theory, because that's what you guys want to talk about, is physics theory of that. So now on this wonderful page, a lone pair does not participate in resonance if it cannot overlap with an adjacent p orbital. It is a localized lone pair. So this is a compound called pyridine, right? Pyridine is an interesting compound. Fun fact, this can disrupt your DNA. It can intercalate between your base pairs, and so you can rupture your DNA. This is a mutagen. And interestingly enough, it has a greater effect on males than females. And I can answer questions about that after we're done with this, in case you're wondering. But here, if you look, it looks like, yes, I can move that lone pair over and I can move my electrons around. It seems like a reasonable idea, right? It looks like this is a very reasonable thing that can happen. But if I was to actually draw the orbitals, if you notice, since all of those carbons are sp2, the way that it is structured, this orbital for my nitrogen, where that is, it's sticking out, right? It's not adjacent. It's not like, see, these 6 are all lined up. These 6 orbitals are all in conjugation with each other. Those carbons are all conjugated. They're in resonance. They're delocalized because they are they line up next to each other. Since this one is not lined up in the same orientation, this is not true. There is no resonance there. I know that this seems confusing. This actually comes from a little bit later when you talk about the aromatic compounds. But in order for something to be conjugated, the atom has to be sp2. It also has to have the same arrangement, right? Those p orbitals have to be aligned, and we don't have that here. Okay, hopefully that makes sense. Again, this is a pretty complex idea. So if you're a little shaky on this, don't worry, we'll come back to it. Like your instructor is going to come back to it. This is something there, all right? Don't assume a lone pair is delocalized just because it is next door to a pi bond. As a general rule, you can assume that when an atom possesses a pi bond and lone pair, they will both not participate in resonance. And as always, if there is no p orbital next door to the lone pair, then it will be localized. So this nitrogen with that green box, the carbon next to it is sp3, right? So there's nothing adjacent. There are no sp2 carbons, right? Here, this nitrogen lone pairs is not localized, but this one is delocalized here. And again, it's just practice as you draw the lone pairs, and it'll make more sense as you practice it. So even though there are 3 atoms in this compound with lone pairs, only the nitrogen here on the very far left is delocalized. It's just practice getting through that. All right, so that's it. That is all the material from everything. So I'm going to stop share and go back. That is all the material that your professor, again, always go to your professor first. I am not your professor, right? I am not your professor. I want to make sure that that is clearly understood. Always go by what she tells you or what he tells you. I am here to help make things make more sense, right? So if I tell you something and you think it contradicts with what your professor is saying, maybe I'm explaining it just a different way, go with what your professor says. They are in charge of your grade. They are in charge of the class. They are the person that's teaching you, right? I am here to help, but I am just a volunteer. I am not the professor in charge. Never, I cannot make this clear enough, never go to her and say, well, I was talking to Dr. Villarreal and he said, never say that. All right, I will disown you so fast. I'm telling you again, your professor takes precedent. She is the number one, or he, if it's Anderson or Dewis, they should be number one in your hearts, right? When it comes to this stuff, listen to them because they are your actual instructor. They are the professor who is teaching the class. I am not teaching your class. I'm just here to help. Just a reminder, if you ever think that doesn't sound like what the professor told me, go with what they said, right? Clarify. And again, never say, well, Dr. V was telling me. Don't do that. Bad idea. But hopefully that has helped. Hopefully you guys all feel more comfortable with this material. Again, it's just going to be practice. All right, so now I'm going to hit stop recording, and that'll be everything for this lecture for organic. I'll upload it next week. I'm going to send a message out and see if you guys want to meet an extra day to have a test review for those of you that are taking a midterm. And we can go over practice problems, or if you have a practice exam, we can work through it.